Welcome back to the class on diffusion in multi-component solids. In next few lectures, we will go over solutions of diffusion equation for various boundary conditions, and Laplace transform will be an important tool in solving these diffusion equations. Last lecture we went through the properties of Laplace transforms, and we also solved some examples wherein we evaluated Laplace transforms for some simple functions. Today we will evaluate the Laplace transforms for some of the important functions that we will encounter while solving diffusion equation. When I say that, one of the important function that we will encounter in solutions of diffusion equation is error function. Okay. So, let us first go over some of the properties of error function, the definition first, and it will be sufficient for this class to just know the definition and some of the properties of error functions. We do not need to go over in detail into this error function. So, the error function is defined as error function of t is equal to 2 over root pi integral 0 to t e to power minus u square du. So, this is the integral over the limit 0 to t of e to power minus u square du, and it is multiplied by the factor 2 over root pi. So, this is the normalizing factor, so that the error function of infinity turns out to be unity, and this is an important function. Many of the solutions will have this error function form. So, let us see some of the properties of error function. First one is that error function of minus t is equal to minus error function of t. It is easy to show. So, for example, if we make a substitution for u equal to minus k, so that when u equal to 0, k equal to 0, and when u is equal to minus t, k equal to t, and also du is equal to minus dk. So, if we define error function of minus t, it should be 2 over root pi integral 0 to minus t e to power minus u square du. Now, if we substitute u equal to minus k, this turns out to be 2 over root pi integral 0 to t, because when u is equal to minus t, k is equal to t, and u square becomes k square, and du is minus dk. So, there will be a minus sign here, and so we see that error function of minus t is nothing but minus error function of t. Similarly, the second property is error function of 0 equal to 0. So, it is very easy to see because integral from 0 to 0 should be 0. The third property is error function of infinity equal to 1, and from the first property it will turn out that error function minus infinity should be equal to minus 1. And then the fourth, one of the important property is the derivative of error function d by dx of error function x should be equal to 2 over root pi e to power minus x square. So, these are some of the properties of error function. So, with that, now let us try to evaluate the Laplace transform for error function. So, error function a over root t is an important function which we will encounter in the solutions for diffusion equation. So, let us try to evaluate the Laplace transform for error function of a over root t. So, the problem is evaluate L of error function of a over root t, and by definition the Laplace transform is integral 0 to infinity e to power minus k t times error function of a over root t dt. And if we substitute for error function from its definition, we will get integral 0 to infinity e to power minus k t times 2 over root pi integral 0 to a by root t e to power minus u square du dt. So, there are two integrals involved here. Let us try to rearrange. Integral 0 to infinity integral 0 to a by root t e to power minus k t times e to power minus u square du dt, and there is a factor of 2 over root pi. Let us take that outside. So, now there is double integral we have to evaluate. In this case it is the integral is first with respect to du and then with respect to dt. So, let us try to change the order of integration, so that it becomes convenient to solve. So, in this case the inner integral is with respect to u. So, the limits are defined for u from u equal to 0 to a u equal to a by root t, and the outer integral is for t. So, the limit of outer integral are defined as t equal to 0 to t equal to infinity. So, how do we change the order of integration? So, if we there are two variables here u and t. So, if we plot u versus t, first the inner integral limits are defined as u equal to 0. So, u equal to 0 is basically this t axis to u equal to a by root t. So, the upper limit is defined by u equal to a by root t. So, if we draw a plot of u versus t such that u equal to a by root t, we will get a plot something like this, and this plot defines the upper limit for u here. U is equal to a by root t. And about t, the limits of t are from t equal to 0. So, t equal to 0 is basically the u axis to t equal to infinity. So, the upper limit for t is infinity. If we try to change the order of integration, which means if we first want to evaluate the integral with respect to t and then with respect to u. So, we first have to take the limits of t. Now, in this case the limits of t will go from t equal to 0 to, so if we draw these horizontal lines, the t is bound by 0 on left side and by this plot on the right side. So, this you can also write this equation u equal to a by root t as t equal to a square by u square. So, if we define the inner integral limit as t equal to 0 to t equal to a square by u square, and for the outer integral limit will now become u. So, the u in this case will be bound by u equal to 0 and all the way to infinity. So, u equal to 0 to u equal to infinity, and the integrand is e to power minus k t times e to power minus u square dt du. We have changed the order of integration, and there is also a factor of 2 over root pi outside. So, let us try to evaluate this inner integral now. So, the inner integral will be integral 0 to a square by u square e to power minus u square times e to power minus kt dt, and this should be equal to e to power minus u square by k e to power minus kt from 0 to a square over u square. So, this should be equal to, and there will be a minus sign here because constant is minus k here. So, if we substitute for t equal to 0, this becomes 1, and for t equal to a square by u square, this becomes e to power minus k a square over u square, and with this negative sign outside, if we remove it, it becomes e to power minus u square by k times 1 minus e to power minus k a square by u square. So, the Laplace transform of error function a by root t should be equal to 2 over root pi integral u equal to 0 to u equal to infinity. We evaluated this inner integral, which should be e to power minus u square by k minus e to power minus u square by k times e to power minus k a square by u square du. So, if we evaluate this separately, this will be 1 over k 2 over root pi integral equal to 0 to infinity e to power minus u square du minus 1 over k 2 over root pi integral 0 to infinity e to power minus u square times e to power minus k a square over u square du. 2 over root pi, the first integral here by definition is 2 over root pi integral u equal to 0 to infinity e to power minus u square du is error function of infinity, and we know error function of infinity is 1. So, the first term here is 1 by k, and we have to evaluate this second integral here. So, let us call this integral as I. So, this should be equal to minus 1 by k 2 over root pi I. So, I in this case is equal to integral 0 to infinity e to power minus u square e to power minus k a square by u square du. And if we notice, the integration is with respect to u and it is a definite integral. So, I is a function of k. So, we write I of k. So, to evaluate this integral, let us try to do a little bit of manipulation. If we take a derivative of I with respect to k, so d I of k by dk, that should be equal to 0 to infinity e to power minus u square times d by dk of e to power minus k a square by u square du. And if we evaluate the derivative of e to power minus k a square by u square and substitute 0 to integral 0 to infinity e to power minus u square times minus a square by u square e to power minus k a square by u square du. So, di by dk in this case is minus a square integral 0 to infinity e to power minus u square times 1 over u square times e to power minus k a square by u square du. Now, let us make a substitution here. So, if we define root k a by u equal to x, which means dx is equal to minus root k a by u square du. In other words, du is equal to minus u square by root k a dx, and if we substitute in this, di by dk should be equal to minus a square integral, and if we see the limits, when u is equal to 0, x will tend to infinity, and as u tends to infinity, x will tend to 0. So, these limits are reversed from infinity to 0, and e to power minus u square in this case will become k a square by x square. So, e to power minus k a square by x square times 1 over u square times e to power k a square by u square. From this substitution here becomes e to power minus x square, and if we substitute for du, that will be minus u square by root k a dx. So, this u square here will get cancelled, two negative signs will become positive, but then this integral is from infinity to 0. If we make it 0 to infinity, there will be a negative sign again, and so we get minus a by root k integral 0 to infinity e to power minus x square times e to power minus k a square over x square dx. And if we closely look at this integral e to power minus x square e to power minus k a square by x square dx in the limit from 0 to infinity, it is basically the same as I of k. So, what we get here is di by dk is equal to minus a by root k times I. Now, if we solve this equation, the solution for I is I equal to c exponential minus 2a root k, where c is a constant. Now, to evaluate c, if we substitute for k equal to 0, then we know I of 0 is equal to, in this case it will be c, but if we substitute in the integral from 0 to infinity e to power minus x square dx, and this should be equal to root pi by 2. 2 over root pi times integral 0 to infinity e to power minus x square dx is nothing but the error function of infinity, which is unity. So, the value of this integral becomes root pi by 2. So, c is root pi by 2, and the solution for I becomes I is equal to root pi by 2 exponential minus 2a root k. So, we have now got the value of I. So, if we substitute back in this equation here, 1 over k minus 1 by k 2 over root pi times I, and I is nothing but root pi by 2 exponential minus 2a root k. So, Laplace transform of error function of a over root t should be equal to 1 over k minus 2 over root pi into 1 over k times root pi by 2 exponential minus 2a root k. So, this root pi by 2 and 2 by root pi will cancel, and we get Laplace transform of error function a by root t should be equal to 1 by k minus 1 by k exponential minus 2a root k. We got the Laplace transform of one of the important function here. If we evaluate the inverse Laplace on both side here, then on the left hand side the inverse will be just nothing but error function a by root t is equal to, on the right hand side will be L inverse of 1 by k minus L inverse of 1 by k exponential minus 2a root k, and L inverse of 1 by k is nothing but 1, because the Laplace transform of 1 is 1 by k, and if we rearrange we find L inverse of 1 by k exponential minus 2a root k should be equal to 1 minus error function a by root t. This is an important result, because when we solve diffusion equation we will do that Laplace transform, and to get back the original solution when we take the inverse Laplace we will have to refer to such this kind of solutions, and so this is an important result here. 1 minus error function is also referred to as error function c or complementary error function. So, right hand side can also be written as error function c of a by root t. So, this is one important formula that we have obtained. So, we have now derived the formula for Laplace transform of error function of a by root t, where a is a constant. So, let us try to now use the property of Laplace transform of derivative of functions and try to derive one more formula here. So, let us say f of t is equal to error function of a by root t. So, the derivative of f of t will be f prime t equal to d by dt error function of a by root t, and we know d by dx of error function x is equal to 2 over root pi e to power minus x square. So, here we will have to first evaluate d by dt of a by root t. So, d by dt of a by root t would be minus a by 2 t to power 3 by 2. So, if we now evaluate d by dt of error function a by root t, that should be minus a by 2 t to power 3 by 2 times, now the derivative of error function, which should be 2 over root pi times exponential minus a square by t. So, this should be f prime of t should be equal to 2 cancelled minus a over root pi t to power 3 by 2 exponential minus a square by t. So, now let us make use of formula for Laplace transform of derivative of a function. So, L of f prime of t should be equal to k times L of f of t minus f of 0. Since our f of t is error function a by root t, as t tends to 0, f of 0 tends to error function infinity, which should be equal to 1. So, the right hand side here will be k times L of error function of a by root t minus f of 0 is 1. And we just derived the formula for Laplace transform of error function of a by root t. If we substitute for the Laplace transform of a by root t, that should be equal to 1 by k minus 1 by k exponential minus 2a root k minus 1. So, this k times 1 by k is 1, it will get cancelled with this one. So, what we have is minus exponential minus 2a root k. So, if we substitute for f prime of t here on the left hand side and get rid of the negative sign from both the sides, we find that Laplace transform of a over root pi t to power 3 by 2 times exponential minus a square by t should be equal to exponential minus 2a root k. So, this is one more formula that we have derived, which is the Laplace transform of a over root pi t to power 3 by 2 times exponential minus a square by t. It should be equal to exponential minus 2a root k. If we take inverse on both the side, we can also write this as L inverse of exponential of minus 2a root k should be equal to a by root pi t to power 3 by 2 exponential minus a square by t. So, this is another formula that is often used while solving the diffusion equation. So, we have derived a couple of formulae today. We will stop here for today. Thank you.